Let's say we are going to talk about combustion reaction. What is a combustion reaction? A combustion reaction is a reaction that your compounds or your reactant is going to combine with O2. So anytime you hear combustion reaction, that means whatever you have is going to react with oxygen. When you do combustion reaction of hydrocarbons, that means the compounds that they have either carbon and hydrogen or carbon, hydrogen, and oxygen. The product would always be carbon dioxide and water. So this is just a reaction. When you have the reactants and you have the product. Sometimes the products are given. Other times when it's like based on definition or it's very obvious, you need to know what type of products you will get. So in a combustion reaction of hydrocarbon, you only get carbon dioxide and water. Then you need to go back and balance this equation. When you write an equation, so you want to also include the phases. G stands for gas, and S for solid or precipitate, L for liquid, and you have AQ for soluble in water. Okay, means that it's soluble in water. A symbol of triangle is used for heat. If it's needed, it would be drawn on the top of the arrow. So now we must balance the equation. Why do we have to balance the equation? Because we have to follow the law for conservation of mass. How do we balance the equation? We count. We start counting. For the combustion reaction, it's kind of easier. You have to balance the number of carbon, which you balance from left to right. You have to balance the number of hydrogens, which you balance from left to right. And you have to balance the number of oxygen. That's last actually, and it would be from right to left. So 1, 2, and 3, because I didn't write them in order. How many carbons you have on the reactant side is 1, and you have 1 carbon on the product side. So I'm going to leave the carbon at this point alone. Then I look for hydrogens. How many hydrogens do I have on the reactant side? And how many should I have on the product side? I have, based on accounting, I have like 4 hydrogens on the reactant side, and there's like 1 H2O that shows 2 hydrogens. I'm not allowed to change the subscripts, because if I change the subscripts, like if I put like H4O, that does not make sense. The only thing I'm allowed is to change the coefficient. What are the coefficients? Are the numbers that appear before the compounds and the reactant and product side. What coefficient should I use here? And I appreciate if you just work with me and tell me what coefficients I should use for H2O to balance the hydrogens. Perfect. So we are using coefficient of 2 to balance the equation. Now, after we balance the hydrogens, we go to balance the oxygen. And when we are counting, if you use coefficient of 2 H2O, that means 2 times 2, that's 4 hydrogens. And we have 4 hydrogens. And 2 times 1, that means 2 oxygens. So we have 2 oxygens, basically, it's H2O. But when you put the coefficient of 2, that counts as 2. 2 times 1, 2 times the subscript, whatever it is. Since there's no subscript, that means it's 1. So 2 times 1 is 2 oxygen. 2 oxygens from water, 2 oxygen from carbon dioxide. That is a 2 oxygen plus the 2 oxygen. It adds up to 4 oxygens. So we have 4 oxygens. What coefficient should I use for the oxygen to make it 4 oxygen? And this is O, not a 0. It's 2, right? 2 O2, that would be 4 oxygens. Now we have to go back and make sure that everything is balanced still, nothing changed. Carbon, we have 1 on each side. Hydrogen, we have 4 on each side. And oxygens, we have 2 plus 2, 4 on each side. So the equation is balanced. When you have a balanced equation, Then you want to pay attention to the numbers, specifically the coefficients. When there is no coefficient, that means is 1. So we have 1, 2, and 2. So this equation is balanced. Reading the equation carefully and being able to read the equation is going to make your life very easy, or much easier, because then you understand the ratio between the number of how many of, or how much of the reactant, how much of the product. The unit for mass in SI unit, if you pay attention, go back to chapter 1, it's mole. So if we say 1 mole, that's basically quantity. You already practiced last class, you know how to calculate the mass for 1 mole, which is the molar mass expressed in gram. So we already know the moles. The other way of reading this reaction is based on number of molecules. So if I say 1 methane molecule reacts with 2 oxygen molecule, it's going to generate 1 CO2 molecules and 2 H2O molecules. Well, reading based on molecules, it is correct, and that's what's going to happen. But we cannot work with the molecules because they are not visible to our eyes, and we cannot touch 1 molecule. It's so tiny. The workable number, it would be best to use the moles. So we are going to get used to reading the balance equation based on number of moles. What does it mean? If you read based on the mole, it's going to be 1 mole of methane, CH4 is methane, 1 mole methane plus 2 moles of O2 or oxygen, 2 moles of oxygen yields 1 mole carbon dioxide and 2 moles of water. Now, these numbers, the red colors that I have here, those are recipe for this reaction. The quantitative analysis of a reaction is called the stoichiometry of the reaction. So this is a question for you. If I use 2 moles of CH4, how many moles of CO2 would I get? I already read the reaction for you once. 1 mole of CH4 would give us 1 mole of CO2. If we use 2 moles of CH4, how many moles of CO2? 2. So it's going to be 2 moles of CO2. If we use 5 moles of CH4, how many moles of H2O would we get? Five moles of CH4, how many moles of H2O? Please respond.
6.
I know.
6.
Okay, it's 5.
Oh, sorry.
5 moles of CH4, how many moles of H2O? Where did you get the 6? Did you add 1 to 5?
Yes, that's what I did.
No, don't add 1. It's like you look at it as a ratio, and thank you for responding. Look at it as a ratio. It is 1 mole is going to be 2 water, 1 methane, 2 water, 2 methane, 4 water, 5 methane is going to be
10. Oh,
10.
You doubled it. Okay.
Yes, is a ratio. You're not adding. So the way that it shows on the reaction, this equation actually is, it looks like that is being added, but it's actually is multiplied by 2 because we are using the ratio. For every mole, we get 2 moles of H2O. Now that's what I mean by reading the equation like carefully. So now you could use these numbers as the ratio. So if you use 1 mole of O2, how many moles of CO2 would be produced? 1 mole of O2, how many moles of CO2?
2.
Emission detected at the Mr. Reed.
One
Mhm.
1 mole O2 is going to give how many moles of CO2? We need 2 O2 to get 1 mole of CO2.
Okay.
So since this is divided by half, this is going to be also divided by half. Basically, this is going to be 0.5 moles. Because it's a quantity, as I said, it's just like mass. We could have like half a mole. We could have 0.1 mole. We could have 5 moles. We could have 10 moles and 0.1, 0.2 moles. In the balance equation, the numbers should be whole number. That's proper way of balancing equation. You don't want fractions in the balance equation, but when it comes to to counting number of moles, you could use half a mole, 0.1 mole, and others. So if you use 1 mole of O2, you are going to get half a mole of CO2. Basically, how did I do the calculation? I say, okay, I have 1 mole of O2, and I multiply that by the ratio that is coming from balance equation. I want to convert this to moles of CO2. I would say 1 mole CO2 and 2 moles of O2. This is a definition. Why is definition? Because it's coming from a solid information. It's coming from balance equation. That is a recipe. Everyone believes in that. For every 1 mole of methane and 2 moles of O2, we get 1 CO2 and 2 H2O. And this relationship between all of them is it is valid. So you could use all of them. So you could relate these numbers together. So you can use, this is coming from the balanced equation. So we say 1 mole of O2, and we want to convert the moles of O2 to moles of CO2. So CO2 goes up. Find this ratio find the formula, what you want to convert to and what you want to convert from the balanced equation, right? And then add the coefficient. Okay, so this is definition, and it is coming from the balanced equation. That's how you can calculate it. 1 divided by 2, and it's going to be 0.5 CO2. So this is reading the balanced equation and the relationship between the reactants and the products. So you notice that I'm going to do one more example of balancing equation, because I want you to practice on counting the proper numbers when you are balancing. When it's combustion reaction, you have to go with carbon first, then hydrogen, then oxygen. Just remember, for oxygen, start counting from the product side and then count the one on the reactant side. It makes it easier. For a different type of, I'm going to let's practice one more balancing equation. And this time I'm going to use aluminum nitrate. Plus, let's just do H2SO4. Okay. In this reaction, I have the 2 reactants in aqueous solution form. This is AQ. That means these compounds are soluble in water. AQ, sorry. And when you have these 2 compounds in aqueous solution, in order to write the product, what you do, you go like in, out, out. So you go with the hydrogen, would go with the nitrate. These are the 2 ins, and then out, out. And sulfate would go with the aluminum. Then write the formula. Remember, the charge for nitrate is -1. The charge for aluminum is +3. That's why you learned this before. Hydrogen is +1, and this is a -2. Keep those in mind. You don't have to write it, just keep in mind. So I'm going to write the aluminum with sulfate. If aluminum has a 3+ charge and sulfate has 2- charge, these 2 is not going to cancel each other. So I'm going to have to switch these numbers and say Al2 and SO4 3. Plus, hydrogen is just 1+, and nitrate is 1 minus, I must use one of each. I cannot do like 2 hydrogens with 3 nitrates. It's not going to balance. So you have to be careful with the charges when you're combining the formulas together to write the formula. Then balance it. When you are balancing equation that involves polyatomic ion, is best to keep the polyatomic ion as a package and count it as like how many SO4s you have, like how many nitrates you have. Okay, so don't break it down. Don't count just the sulfur. Don't count just the oxygen. It's going to make it harder for you if you do that for balancing. You always start with balancing metals. Okay, balance the metals, balance the polyatomic ions, but then last 2 things you want to balance is oxygen and then hydrogen. Okay, so how many aluminum do I have on the reactant side? The coefficient is not visible, so that means is 1. I have 1 aluminum. On the product side, I have 2, so I'm going to add coefficient of 2 here to make 2 aluminums. When I do add the 2 in front of the aluminum, that applies to aluminum. So I have 2 aluminum, and then 2 times 3, 6 nitrate. Okay, so I have 6 nitrate. If I was going to count the number of nitrates, next, I'm not going to say I have 3 nitrogen and 9 oxygen. I can say I have 3 nitrates because polyatomic ion appeared both sides. I can combine it. How many nitrates do I have? Here, I have 2 times 3, 6 nitrates. I have 6 nitrates, so I'm going to write 6 right here to make it 6 nitrate. Then I look at the sulfate. How many sulfate do I have? Please help me. How many sulfate I have on the reactant side? H2SO4 has how many sulfates?
Repeat, you said H2SO4?
Yes, how many sulfate do we have? How many SO4s do we have on the reactant side?
Someone says 3. Someone
Just
said
1. On the reactant side is 1. On the product side is 3. Okay. So if on the product side is 3, I want to make this also 3. What should I do? Should I add the 3 here? No, I cannot add the 3 there because that's the subscript. When after I write the equation, I'm only allowed to add subscripts. So I'm going to add, because this is 1 SO4, I'm going to add 3 right here. So 3 times 1 is going to give me 3 SO4 on both sides. Now I have 3 SO4 on the product side, 3 SO4 on the reactant side. There is no oxygen alone for us to count, so we are going to count the hydrogens. How many hydrogens do I have on the reactant side? How many H?
You have 2.
Okay, what about this 3?
Uh,
And if you have coefficient,
6,
that's 3
yeah.
times. So it's going to be 6, perfect.
6, okay.
I have 6 hydrogens on the reactant side, and how many hydrogens I have on the product side. Every time you add a number and then you're counting, you have to count with that number. So on the product side, I also have 6 hydrogens because this 6 was supposed to be right here for the hydrogen. So 6 hydrogen. So if it's 6 hydrogen on both sides, it is balanced. After you examine each one of them and you think everything is balanced, you want to go back and check it again. We have 2 aluminums on the reactant side. When you are counting, is coefficient times subscript, 2 times 1. So this is 2 times 1. In this case, you have 1. That's the coefficient times 1. That's 1 times 2. Still is 2. Okay. For nitrate, I have 2 times 3, 2 times 3 nitrates. And I have here 6 times 1 nitrate. For hydrogen, I have 3 times 2 hydrogens, 3 times 2 H's. And on here, I have 6 times 1 H. So it's 6. For sulfate, I have 3 times 1 3 times 1 SO4, 3. And in this case, I have 1 times 3 SO4. I have never written everything like in this detail. I just want to make sure you know how to count these numbers. Perfect. Do you have any questions about balancing this equation? So first we have to write the proper equation. The products must be proper, written properly. Then we have to balance it to make sure that we have balanced equation. After the equation is balanced, these numbers, they become very important for the stoichiometry of this reaction. Whenever you want to do some calculation, is going to be very important because that is the recipe. This is like you have 2 slices of bread, 3 slices of cold cut, and that's going to give 1 sandwich. Okay, 1 sandwich. So you have to make sure that you know that if you have 4 slices of bread, you can only make 2 sandwiches. But if you have 6 slices of bread, you can make 3 sandwiches you could have. And then when the quantity for one is given, is assumed that the other one, you have plenty of it. Like I didn't say I have 2 slices of bread and I have only, if I say 2 slices of bread and 5 slices of cold cut, what's going to happen? How many sandwiches could I make if I consider this as a sandwich? Just this one as a sandwich. If I have 2 slices of bread and 5 slices of cold cut, I can only make 1 sandwich. Why? Because I'm running out of bread. If I don't have bread, it's not going to make sandwich. And that is going to help you with that idea, is going to help you with the yield of the reaction. What is the yield or theoretical yield of reaction? How much of the product is going to form? And that, in order to know that, we need to know and examine what is limiting reactant and what is the excess compound, which I'm going to move on to the next practice problems. And then, okay, so this is already, all the numbers is counting, all that is here. And I didn't want to start with the solved problems for you to start from scratch. So if you have this balanced equation, you can read based on molecules, 2 molecules of octane, 25 molecules of oxygen would yield 16 CO2 and 18 H2O. Okay. Now, 2 moles of, if you say molecules, you could also, this, which is more, what's more practical to read it based on number of moles, 2 moles of octane, 25 moles of O2 would give us 16 moles of CO2 and 18 moles of water. If you want to use this for conversion, if someone asks you if you have 4 moles of octane, how many moles of H2O you would get? What you need to do is say, okay, I'm only asked about these 2. If I get 2 moles of octane, I'm getting 18 moles of water. If I get 4 moles of octane, then it's going to be double. If I double the octane, I have to double the water also. So that is going to give me 36 moles of water. Or use the ratio, okay? You would say 4 times H2O over octane is going to be 18 H2O over 2. These, when its definition is coming from balanced equation. So it's going to make it easier. You don't make any mistake. This part is definition and is coming from balanced equation. This coefficient should correspond to what you have on the balanced equation. Okay. So if you use 22 moles, okay, if you use 22 moles of octane, how many moles of CO2 you would get for 22 moles of octane? Because then the mental math is not going to be very helpful. You say you want to convert the octane to CO2, so you use that number from the balanced equation. For every 2 moles of octane, you get 16 moles of CO2, and do the math. Okay. When you have a balanced equation, you want to find out how much of the product is going to form if you have the mass. Okay, when you have the mass, let's say estimate the mass of CO2 produced by this many grams of gasoline. We can probably use a smaller number so we don't have to deal with that quantity. Okay, so we can use this one for 9 grams. Okay, let's use this example. It's the same. The concept is going to be the same, but it's going to help us to move faster while in class. So this question says, according to this equation, how many milliliters of water are made in the combustion of 9 grams of glucose? If the quantity only for glucose is given to you, that means you have plenty of oxygen. So you don't have to worry about oxygen. So the equation is already balanced. If it's not balanced, you have to balance it. Since the value or the mass for this is given for glucose, I'm going to mark this as a given. And it's asking for water. So I'm going to mark this as looking for. Okay, we are looking for something about water. The quantity for this one is given. Since these coefficients are showing mole, they don't show mass. Mass is given. My step 1, I have to convert or find moles of given. Okay, find moles of given. Step 2, I can use the balanced equation. If for every 1 mole I'm getting 6 mole of H2O, then I can convert the number of moles of given to moles of looking for. So step 2, use balance equation to find moles of looking for. Okay, let's do that step. We are going to start with the 9 gram, 9.0 gram of glucose. And if I have 9.0 gram of glucose is a C6H12O6, I would multiply by, how can I go from mass to mole? What information do I need? I'm converting from mass to mole.
You put 1 mole on the top.
Perfect. 1 mole of C6H12O6 over 180, which is the molar mass. That's the molar mass since it's given. So we just use that. 180 gram of C6H12O6. So what I did here, I canceled the gram. I have the mole. What's the next step? On the next step, it says use the balance equation in order to convert the moles of glucose to moles of water. What ratio should I use? It's coming from balance equation. I already know that I'm only dealing with these two. I want to convert from glucose to H2O. So H2O has to be on top and glucose needs to go down. Now, the coefficients is coming from balance equation because the instruction says use the balance equation, and you are going to remember that this coefficients always is coming from balanced equation. And then you find that number of moles. When you find the number of moles, step 3 is going to be answer the question. Okay, step 3, answer question. What is the question? Question is asking for how many milliliters of water. Well, based on this calculation, I can't get the milliliter yet, but I can get the mass. If I have the moles, this is moles of H2O. I can get the mass of H2O. How can I go from moles of H2O to mass of H2O? I have the moles and I need to go to mass. 1 mole H2O is 18 grams of H2O. And with that, I can convert the moles of H2O to mass of H2O. Now that I have the mass of H2O and I know 1 milliliter is 1 gram, I can convert mass to milliliter using the density. So if I find here, if that number is 5.4 milliliter, 5.4 grams, I'm going to write here, 5.4 grams H2O. I can write here, I can add another fraction. You say 1 milliliter over 1 gram, or say 5.4 gram times 1 milliliter over 1 gram H2O. This is gram H2O. And that would give me 5.4 milliliters. So what I want to emphasize here is that if you have the mole of the reactant, you can use the balance equation to find mole of the product. If you have the mole of looking for, or the product, you can answer multiple questions. What can you answer if you have the mole? What type of questions you can answer if you have the mole? If you have the mole, from mole, you can go to mass. You can go to particles. You can go to molarity. You can go to mole of others. So you can answer multiple questions. Now, how do you go from mole to mass? From mole to mass, what do you use? Molar mass, right? You multiply by molar mass. How do you go from mole to particles? You would use Avogadro's number.
A quick question. So,
Yes.
yeah. Okay. No, continue. Never mind.
Yes. If you have the mole, you can use molar mass to go to mass. And this question specifically was asking volume, then you have to use the density to convert to volume. So if you have the mole to go to the particle, you would use Avogadro's number. If you have mole, you want to go to molarity, you are going to divide that by volume in liter. Okay? If you divide by volume in liter, you would change to the molarity, because definition for molarity is number of moles divided by volume in liter. Moles of others in the reaction, you are going to use the balance equation. Use balance equation. use balance equation. So you use the ratio, okay? Ratio or mole ratio. Use mole ratio from balance equation to go to the moles of others. So the point of is that these reactants and products, they are related together based on those numbers that you have and the coefficient, and that shows like the recipe for this reaction. You could extract like multiple ratios here. You could say for every 1 glucose, I need 6 oxygen. For every 1 glucose, 6 CO2 is produced. For every 1 glucose, 6 H2O is produced. For every 6 O2, I can get 6 CO2. For every 6 O2, I can get 6 H2O. So these are the ratios. If you have the mole of given, you can find the moles of looking for. And in order to find out which one is given, which one is looking for, you just have to read the equation carefully, read the problem carefully. I want to answer your questions before I move to the next slide. What is your question? If there is any question, please let me know. Questions? No? Okay. So this slide, it shows the solution for what we had up there, all in one step. Up to here is step 1, which we had, find the moles. Okay, step 1, find the moles of, this is the moles of given. Sorry. Moles of given. And then next step, you're using this ratio from the equation, find the moles of looking for. Step 3, you're answering the question. You want to find the volume, but you need to get the mass first. If you have the mole, it's very easy to go to the mass. I mean, that's not after you had your experiment 4 and you had earlier about this unit 5, you know how to go from mole to mass and mass to mole, and then particles. That part, it should be solved already. And since you have the mass, to go to volume, you would use density. So you're using density for this. You're using molar mass of looking for. Okay, how do we find out? Then there was a question about the reaction yield, which is going to be determined by limiting reactant. If you have 2 reactants, one is going to be limiting, the other one is going to be excess compound. If they don't say anything about the other compound, okay? If like here, if they just ask about the mass of glucose, they give you mass of glucose, they don't say anything about oxygen, assume oxygen is limiting. But if they give you the quantity for both of them, then you have to decide which one is going to be consumed first. Then for that one, you have to find out, rely on definition for limiting reactant. What is limiting reactant? Limiting reactant is going to be consumed first, is going to determine how much of theoretical yield you will get, because when you do experiment or when you do synthesis, there would be some loss of the product, and unless you have 0 error. Okay, if you have 0 error, you would get 100% yield. But the actual yield that you get, you measure on the scale, is normally or often less than what theoretically on the paper you could do the calculation. The theoretical yield comes from calculation using the limiting reactant, saying that, okay, if you have this much of a compound, how much of the product I will get theoretically. And we do the calculation. We just did the calculation for water, the mass of water or the milliliter of the water. That's basically the theoretical yield. And we do more example of that. Actual is like if you get the water and you measure and it's like instead of 5.4, if you had like 5.2 grams, that's actual. You can't change that. You just take that and use as actual. Actual divided by theoretical, it would be the percent yield. But how do you find the limiting reactant? The limiting reactant is the one that is going to be consumed first, or is the one that is in less amount based on the stoichiometry of the reaction. Okay, based on the stoichiometry of the reaction. If we have, let's look at this example. We have 5 molecules of H2O and 8 molecules of O2. Okay. We are going to look at this like when the numbers are this small, we can do like mental math. Okay, we can do mental math. For one CH4, I want to see how much of CO2 I will get based on CH4 and O2. Okay, if I use one CH4, I will get one CO2. For 2 oxygen, I get 1 CO2. Now, these are the numbers given. I want to see how much of the product would I get, and the product, I'm just assuming the CO2 as a product. If I use 5 molecules of CH4, how many CO2 would I get? For 5 CH4, how many CO2 would I get? Answer, please. I know you have this answer. You already know this. For 5 CH4, how many CO2 would I get? What's the ratio? Did you answer and I can see it, or you have not answered? 5, thank you. So for 5 CO2, I'm sorry, for 5 CH4, I will get 5 CO2. Perfect. If I use 8 molecules, 8 O2, how many CO2 would I get? How many CO2 would I get? For 8 O2. For every 2, I'm getting 1. For 4, I get 2. For 6, I get 3. And for 8, I will get 4. Thank you. So I will get 4 CO2. Which one produces less product? The one that produces less product, that is known as the limiting reactant. Okay, that's the limiting reactant. In theory, I should get, if I mix these two, in theory, I will get 4 moles of CO2. If I want to get the mass of that, I'm going to multiply 4 by molar mass for CO2, which is 44. Then I get the mass for CO2. What you find, the amount of the product you find by consuming all of the limiting reactant, that is known as theoretical yield. The actual is what you find in what is given. If they say like the person, sometimes they name this student got this much, or this person got this much, that is actual. Theoretical, they don't have to give it to you. You should be able to do the calculation for theoretical. Okay, let me bring the next slide because I think there was an error there. 8 molecules of that. This is going to be, it's wrong. For every 1 CH4, you're getting 1 CO2. So that's the one that I need to correct it. This is 1. It's not going to make a huge change here. So you would get 8 CO2. And for 10, you would get, that's 1 CO2. For every 2, you would get 5. Okay, still the limiting reactant is oxygen, but I just want to make sure that this ratio is corrected here. So we know that O2 is the oxygen is the limiting reactant, and there would be some excess of CO2 left over. So you would get some CO2 left over.
Sorry to interrupt, Professor. Just to confirm, did you say that the theoretical then would be the limiting reactant?
The theoretical is going to be determined based on consuming the limiting reactant. So basically, in theory, we will get 5 moles of CO2 only. That is the theoretical yield. And I can do example. Let me just go over this example quickly so we can get the. Let's see if I have another example. Smaller numbers. Okay. How many grams of N2 can be made from 9 grams of NH3 reacting with 45 grams of CuO? And I do need your help. Please use the calculators, your calculators. What is we given 2, we are given both reactants. If 2 reactants is given, you can't use those steps that I gave you, step 1, 2, 3. Step 1 here would be determine which one is the limiting reactant. In order to determine which one is the limiting reactant, you need to convert both reactants, the mass for each one convert to mole. So we are going to say 9.5 gram of NH3 times 1 mole. Any of these steps you have question, you have to stop me, okay? Because I assume you already know how to convert the mass to mole. 17 gram of NH3. And where is this coming from? That's the molar mass for NH3. And that equals, give me the number, please.
.53.
Thank you.
Yeah.
0.53 moles of NH3. Okay, moles of NH3. And how much of N2, how many moles of N2 this is going to give me? I'm going to multiply that by that ratio, 1 N2 for every 2 NH3. And I'm going to have to take this off because it's not equal. And that is going to be how many?
Repeat that, please.
0.266 mole of N2, right? Now, if we consume 45 grams of CuO, 45.2 grams of CuO, first of all, we need to know how many moles would that be, times 1 mole over, what's the molar mass for CuO? Is it 79? 79 grams, like 63. I could put 80, 64 plus 16, 80 grams, or 79.5 to be more grams of CuO. This is the molar mass for CuO again, okay? That's the molar mass for CuO. That equals, give me this number, please.
0.57.
Okay, divide by 79.
Yeah, 0.57.
Equals 0.57.
Mhm.
Okay, this is the moles of CuO. In order to find the limiting reactant, we want to see if we consume this, how much of N2 we will get. For every 1 N2, we need 3 CuO, and that equals
0.19.
0.19. This is going to be mole of N2. Now, when you get to this point, you examine and you find out which one gives you less product. Which one is giving you less product, CuO or ammonia?
CuO?
CuO gives you less product, right?
Yes.
Because CuO gives you less product, then CuO is going to be the limiting reactant. Now we have the limiting reactant. Now, if we were going to find the theoretical yield, we can start from here, from the limiting reactant. We said the limiting reactant is giving us this much of the product, but that's expressed in mole. If we convert this to gram, that is going to be theoretical yield, is the mass of the product based on limiting reactant. So if I have 0.19 mole N2 times 28 grams over 1 mole. And where is this 28 is coming? This is again the molar mass for N2, N2, molar mass for N2. And that equals
5.34.
5.34. 34?
Yes.
Okay, 34 grams. If the actual yield, there was actual yield given in this problem and says that one student did this experiment and found 4.9 gram of N2. Okay. If they say they found 4.9 gram of N2, this is the actual. But this one is theoretical yield. In order to calculate the percent yield, you would do actual 4.9 divide by 5.34 times 100%. And the number, what would be the percent? Just divide it, please. Is 4.9 divided by 5.3.
Oh, wait, Professor.
Yes.
It wasn't 5.34. Like someone said, it was 5.32.
It's okay. It's not going to make a huge difference at this point, really. So it's going to be 91%. So if this is a 2, it's going to be 2, and then 4.9 divided by 5.32 is going to be 92%. So if you change this one to the 2, is going to be 92%. Even for multiple choice questions, you're not going to get the answer of like a 91% and then 92%. You probably get like 92%, and the other one would be like 9%. The other one would be like 48%. So you should be able to still answer the questions. But what's important to get to the definitions and being able to read the reaction. Like what is happening here is that you have a balanced equation that is saying for every 2 moles of ammonia and 3 moles of copper oxide, this is a copper 2 oxide, we get 1 mole of nitrogen gas, 3 moles of copper, and 3 moles of water. They gave you 2 reactants, but the concentration is only on 1 product. So you don't have to worry about any of these. Okay, you're just using this ratio of 1/3 for copper oxide, 1/2 for ammonia, and the best communication between the reaction when you have balanced equation is number of moles. It's not easy to communicate with gram. It's doable, And some high school professors, teachers would use the grams, but it's easier to communicate with moles because balance equation is expressed based on mole or molecule. Molecule are not easy to work with. Mole is easy to work with. So we are going to work with moles. So if you want to say how much of ammonia you have and how much N2 you get, make sure you express that in moles. That's why we do here. First step, we convert the mass of ammonia to mole of ammonia. Then we say, if we have this many moles of ammonia, how many moles of nitrogen should we get? And if you have in the mole step, you can compare the number of moles of the product and determine which one is lower in order to find limiting reactant. You don't have to calculate all the way to the mass. That's like extra step. As long as you have moles of nitrogen, you can compare the two. The one that gives the least amount of product, that is limiting reactant. So you already have the moles of the product. You change that to mass of product, that would count as theoretical yield. When you have theoretical yield, if the actual yield was given, in this question was not, I just added to practice. If the actual yield was given, you divide the actual by theoretical times 100% to get the percent yield. Question, did I answer your question about the finding limiting reactant and the
just sorry, I think I missed it, or I was doing the calculation on how you got the 4.9 over 5.32.
Okay, the 4.9, that was like, it was kind of added, as I just explained, that number was not provided in this problem, but I said if, okay, I said if actual yield was 4.9 grams, then what is percent yield? Okay, I added that in addition to this problem, because if we know that we get 5.3 grams of nitrogen, this is in theory, so this is the theoretical yield. If you have the actual yield, you can calculate percent. If the actual yield is not given, you cannot calculate percent yield. So percent yield, it was addition. Percent yield equals actual over theoretical times 100%. Is it clear now?
Okay, yeah, I got it. Thank you.
Okay, perfect. It was just the addition since it was not part of the problem, and it's good that you brought it up. Okay, we did talk about the solubility beginning of this last week, and I want to just make sure that when we say soluble, if it's two compound, two liquid, it's going to give like one phase. If it's solid and liquid, the solid would disappear. So solubility, we have like solubility rules or solubility table that can help you to predict what is soluble, which ionic compound is soluble, which ionic compound is insoluble. So based on reading this line, if I read here that any compound containing sodium, okay, it doesn't just say sodium, but I'm just using sodium as an example. Any compound containing sodium is soluble with no exceptions. Here's exceptions with no exceptions. So if someone tells me like sodium, and then I don't know the other part, okay? So even if you don't know the other part, I know what the other part is, like sodium phenoxide. If someone tells you, is sodium phenoxide soluble or not? I don't have to know what phenoxide is because it's an organic molecule. You may not know it in 1045. As soon as you see sodium, this compound contains sodium. So you say, yes, it's soluble. So if it's sodium chloride, bromide, sulfate, nitrate, nitrite, phosphate, phosphite, any compound that contains sodium is going to be soluble. Same thing for nitrate. Any compound containing nitrate is soluble with no exceptions. So it could be sodium nitrate, lithium nitrate, potassium nitrate, magnesium nitrate, calcium nitrate, anything. As soon as you hear nitrate, soluble. Nitrate is soluble. Acetate, this is also negatively charged anion. So positively charged ammonium acetate would be soluble. Potassium acetate, soluble. Sodium acetate, calcium acetate, any acetate is soluble because I see this key point here, no exception. Anything contains any of these is going to be soluble. Now, when it comes to this, being able to read, what does it mean? It means that AgCl is solid, not soluble. Cl with any of these, okay? With any of these. Then Br with any of these, not soluble. It's not that you have combination of those. So if you have silver with iodine, because it's silver with iodine is not soluble. So you put S. A bromine with lead, Pb, Br2 is solid, is not soluble. So any combination of these two columns is going to be not soluble because this is exceptions to the solubility. Okay. When it comes to sulfate, sulfates, it says most of sulfates are soluble except for these. Okay, except for these. What does it mean? That means that silver sulfate is going to be insoluble. Calcium sulfate is insoluble. But if I bring like potassium sulfate is soluble. How do I know it's soluble? Because potassium is not one of these. That's how you use this table. Any questions about using the table?
Is there a way we can memorize this or like
The only one that you should
familiarize?
memorize, the only one that I would tell you to memorize these. Memorize these. This is the only one to memorize. Don't worry about memorizing others. They would be provided to you.
Okay, thank you.
Okay? But memorize these. Don't expect that if compound contains sodium, potassium, because these are limited and there's no exceptions. Only these memorized, only that part, please. Everything else would be given to you. Okay, these are the compounds that are mainly insoluble except with these. We already knew this. If it's lithium, sodium, potassium, or ammonia with anything is going to be soluble. So these are mainly insoluble. So that means if you have calcium sulfide would be insoluble. If you have sodium sulfide, it would be AQ because sodium is one of these. I'm sorry, calcium also was in there. I didn't see it. But if you have magnesium sulfide, it's going to be soluble because magnesium is not one of these. So it would be solid, not soluble. The S in a chemical reaction is for solid or precipitate. That doesn't dissolve. AQ is for soluble. S is, sometimes in an experiment, you would designate, oh, this is soluble. So you put S and you put I for insoluble. So in a chemical reaction, in aqueous chemical reaction, S stands for solid or precipitate. The other alternative for that, it would be a drop like this, arrow down. Questions?